I doubt it. Not for the exam. Guys, do you have, Colin was saying you were doing something recently with codons, is it?
Yeah.
Yeah. Do you have the table he gave you where...
He didn't give us, it's already in the book.
It's in the book. Okay, can I see it?
Because yeah.
We had the biology lessons.
No, I went back.
Is there a table where the totals are?
Fair enough.
That's the table of the protein.
No, ours is a long
He doesn't have a table where he counted up how many they appear. No, not that.
Is it? Nate, remember the last week's tutorial? Do you have that?
Yeah, it was something where he said he was counting how many...
Yeah. Do you have that?
No.
Does anyone else in the group might have it? Anyone else might have it?
Maybe someone Amy.
No? Ah, it's okay. No, it's alright.
But in our pronunciation, it's
Why can't I log in? Alright guys, I need you to open, I'm trying to open it too, the formula book that you had for the last class. Oh, here we go. Yeah, the thing you were using.
okay. See?
Right, here we go. Carol, did you open the formula book?
Yes, sir.
Okay, thank you. Okay. We'll see, just relax. Okay, so... Now, what we're having a look at is... No, we did binomial last time.
Probability. Normal distribution.
Okay. Come on. Can we see? Yeah.
Wait, I have this.
Yeah.
Is standard normal distribution the same as polynomial?
No, we should go back to it. David, come on.
What's the difference?
Guys, come on. You haven't done it yet. We'll do it soon. Okay? Yeah. So, guys, come on, please. So what we're having a look at is chi-square test. So last time we were doing binomial testing, and binomial testing usually comes up when you're testing if you have the right number of successes or failures for our hypothesis. Remember, so we did examples with like the tea drinker and the psychic and all this. 138. It's the next page from yesterday. Right, chi-square test. So, when do we need chi-square tests? Chi-square tests come up when we want to test... Yeah, what do you think it is?
Correlation?
No, not correlation, really. Chi-square test comes up when you have a theoretical amount that you expect to see versus what you actually get from an experiment. I'll give you, like, the reason I was asking about the biology one was because Colin was telling me that recently you did something like codons, is it? And you can have them encoded, I'm not sure about this, you can tell me, encoded different ways. Like he said, there's like 4 different types or something. Do you know what I'm talking about? Yeah, and he said you might think that they show up equally likely, but they don't. There's one that's it's one that's favored. Yeah. So this is actually a good example of a chi-squared situation, where you have in your mind a hypothetical, a theoretical, that they should all be equal. Then you have some actual data, and then you want to know if your hypothesis is right or not. So I'll give you like a very, very simple example. Imagine you were to flip a coin 100 times, for example. So let's say we have heads, and let's say we have tails. And let's say we get 50-50. Now that's exactly what you expected, isn't it? So if your hypothesis was that the coin is fair, do we reject or not reject that? Not reject it. Okay. What about if it was, say, 55-45?
What's fair?
We don't know yet.
Yeah, at some point, the numbers become so different to what we expected that we start to doubt the hypothesis. Yeah, well, we could do the calculation, okay? But what about a situation that's not binomial? Because with the coin it was binomial. So what about a situation like with the die? Well, how did we deal with the die in the last class? We broke it into a binomial, didn't we? We said, for example, getting a 6 is a success, and not getting a 6 is a failure. But we now want to be a little bit more precise, because we can't always do that. For example, maybe this one here I have 10, 10, 30, 10, 9, 31 or something like this. Is this looking like it's fair? No. And we can't really do the binomial trick. I mean, we would have to say getting a 3 or a 6 is a success, but now it's getting a little bit messy. So, back to just saying about the chi-squared. The chi-squared works when you have 2 things. You have an expected, so you might want to write this down, expected number, frequency, and then you have an observed number, and that's also a frequency. So the coin is a good example. How many heads and tails do we expect in 100 flips? 50-50. No, leave it, it's fine, it's fine. Okay.
What do you mean by frequency?
Yeah, well, I'll do an actual example now, okay? Does anyone have those numbers from the tutorial with column, the table with the 4 possibilities and how many times they appeared in each possibility? Do you know what I'm talking about?
Well, that's it.
Is the totals there? Yeah, you have them? Oh, great. Great. So these are
codons, so these are the frequencies.
there's 16.
Yeah, and these are the different species.
Oh, I see. This is one species and the 4 codons, and then a different species and the 4 codons. Yeah, okay. Great. I'll use this as an example. Now, guys, please, just focus on your maths, okay?
I'm waiting for you.
Now, I need to give you a formula. The formula is in the formula book. I can show you where it is. It is, yeah, this one here. Now I'll explain how it works. So the formula is chi-squared equals the sum of the difference between what was observed and expected squared all over what was expected.
What's the formula?
here has a
L.
7. Okay. Can I do an example of how to do a chi-squared? Yep. So, I'm going to take the example that you had from columns class. Here's my data for our first example. Species Rn, what's it, like ratter or what? What's species Rn? Okay, species Rn. And there were, are these 4 codons?
Yeah.
Or whatever it is. CCC, CCG, CCU, is it? Yeah. 7, 12, 2, and 4. How many is that altogether now? 19, 25, is it? Yeah? Is it 25?
Yeah.
Now I'll just make this tree just for our first example, just to make it a little easier. Okay. So, what is our hypothesis here we would like to test? We want to test the hypothesis that each
It's 25%.
codon, what's it, C-O-D-O-N? Each codon appears equally likely, appears 25% of the time. I don't know what the precise biological phrase is. Is it, what's it, not materialize, express, is it? Each codon expresses, is it? You don't know? Fine, okay. Now,
Why 25%?
that's the hypothesis I'm testing that Columns suggested in class, that you might think they show up equally likely. Each one shows up 25% of the time. So, the alternative here would be not this. That there are not equally likely. Okay? Now, let's do the calculation. Let me show you how this works. So what you do is you have to make 2 tables. The first table is what you observed. So I'll call this table O. And that's 7, 12, 2, and 3. Then you need to make a second table of what you expected if the hypothesis, the null hypothesis, was true. So if the null hypothesis was true, how much did you expect each one to show up by? 6 times. That's what you expected. You know, if you had, 24 divided by 4, you expected each one to show up 6 times if it was equally likely. Now we can kind of tell that, yeah, okay, this is actually quite different, especially the second guy. It's much more. But we want to make sure. So, we calculate the chi-squared. And what you do is it's the difference between expected and observed squared. So the difference between 7 and 6 is 1 squared, 1, over the expected. Plus the difference between 12 and 6? 36. Yeah, 36 when you square it over what you expected, 6. The difference between 2 and 6 is 4. Squared is 16 over what you expected. And then 9 over what you expected. What's that, please? Can someone total that up for us? 24, 51 over 6, is it? Can someone give me that as a decimal, please? I need it as a decimal.
Why we got the 6?
10.3.
The 6?
Yeah.
There's 24. So, a quarter of 24 is 6. If they're supposed to be equally likely.
You mean the total of the numbers?
Yeah, this is total 24, I hope. Yeah. What is it?
10.3.
10.3 recurrent. Okay, fine. Fine. Now, this one is a little bit different to what we did last class. You don't know the p-value. What I mean to say, sorry, is you can't calculate the p-value. Instead, we have this table at the end. Now, for this course and most research you do, you actually only need this column here Can you see that? The one that has 0.05 on it? And the reason for that, do you remember in the last class, was because we said 5% is the threshold p-value here. So all the rest here we don't really care about. Now, we need to look at the right number here for what's called the degrees of freedom for our problem, which I'll explain how to get here.
Is it 0.5 or 0?
0.05 for 5%. Okay. Yeah.
Can you remind me the meaning of the HO and hypothesis, the types?
Null alternative. Remember those words? Yeah. Okay. So, what this table is giving you is the biggest chi-squared value you can have before you reject. Let me give you an example here. Imagine that this guy was 0. If this was 0, then what must have happened here? If we got a total of 0 here, what must have happened here? They all... Yeah, what numbers here? What numbers? 6, yeah. Because... Yeah, this would have to be all 6s so that this would all be 0, so this would be 0. Okay? So in other words, the bigger this number, does that give us more confidence or less confidence that it's the same? Less confidence. I mean, at some point these are going to be so different and this is going to be so big that we just say, no, it's impossible that they could be the same. Okay? So these values here represent the threshold of believability. At what point do we say, okay, the chi-squared is too big, reject the hypothesis? So we need to look up degrees of freedom for this problem. Degrees of freedom. Now, this is the only complicated idea really for this lesson, so just pay attention carefully. You go back to the data here. Imagine you've done this experiment, and your experiment is you take a sample of 24, whatever the heck, what are these called? Codons? Okay. A sample of 24 codons, and you count the appearance of each. This is called codon as well? There's no different? Okay, fine. There has to be some adjective to make this different to this. Like this is generic codon and this is particular codon? Like,
Unless you want to name the
Is it
exact
protein?
amino
Is it the types of protein?
Or something.
oh wait, whatever, fine, okay. Anyways, so you do the experiment, you get 24 codons. So when you look at these 4 numbers, this number could have been different, right? Of course it could have. We call that 1 degree of freedom. This number here, that could have been different, 2 degrees. This number here could have been different, that's 3 degrees. This number here can't have any degrees of freedom.
How does that could be different?
Well, you do the experiment and you get different numbers, right? Whenever you do an experiment, do you ever get the exact same numbers?
No.
No. So it could have been different.
So the last number, it doesn't have degree of freedom because like 24
So
minus.
there-
Yeah, that's it, yeah. Yeah, the last one doesn't have any freedom because whatever value was set for the first 3, that it's set for the last one because the total has to be 24. In other words, only 3 of these 4 numbers can actually change. The 4th number gets fixed because the total in the experiment is 24. So there's only 3, what you might call variables, 3 degrees of freedom. Okay? Now we'll do another example, don't worry, but here the degrees of freedom is equal to 3. So you go to your table and you look at number 3, and what number do we have here? 7.81. Now, are we more than or less than 7.81? We are 10.3 is more than 7.81. It is too big. Therefore, we reject the null hypothesis.
What do you think?
Where did you begin?
Oh, okay, just listen.
Oh, because the 3 is fixed.
No, listen. Listen carefully. And the moment you don't understand something, you need to stop me so I don't have to repeat the whole thing. And this goes for everyone. I'm going to repeat the degrees of freedom, and the moment you don't understand something, you need to tell me, because I'm not going to repeat the whole thing again a 3rd time. Okay? Right. So, your experiment is to measure or count how many of these guys you have from a sample of 24 codons. Each time you do this experiment, in real life, these numbers will change. This first number, maybe it's 7, maybe it's not. So we say that this has freedom. Has freedom. It can change. Yeah. The second number, could it be 12 or could it be different? Yeah, it could be different again. So this one has freedom. And likewise, the third one has freedom. However, the fourth one has no freedom because whatever numbers are here, for example, if this is 10, 10, and 2, then I know the last one has to be 2, because the total is still 24. So there is no freedom here. There is only freedom here, here, and here. 3 degrees of freedom.
But I mean, like, if you go 2, it's still 24.
If I put this 2 here?
Yeah.
Yeah. It has to be 24. It has to be 2, right? It can't be any other number.
Yeah.
Suppose you're telling me you did the experiment again.
Okay.
And you tell me, Stephen, guys, listen. Listen. Suppose you did the experiment again. You said, Stephen, I remeasured 24 different samples. And I didn't get 7, instead I got 10. And I didn't get 12, instead I got 10. And I didn't get 2. Oh no, I got 2. Okay, I got 2 again. Fine. So I'll make it different. I'll make that 3, just to be different. Okay. I would tell you at this point, stop. You have given me enough information. I know automatically what the last one is.
Yeah, it should be.
Should be 1.
Yeah.
Yeah. So only 3 of these can actually change.
Yeah.
The fourth one has no freedom. It's fixed because the total needs to be 24.
Do you have
So
to
does
go in
it-
Wait.
order?
Say again?
Do we have to go in order?
No, it doesn't matter. You could have done it the other way. You could have told me this one, and this one, and then this one has no freedom. So no matter what way you do it, only 3 of them have freedom and 1 of them doesn't. Yeah?
DOF stand for?
Degrees of freedom.
Each is 3 plus each of them have freedom.
Yeah. Yeah.
But if
And it doesn't matter which 3, it's just 3 of them. Yeah.
Okay, yeah.
Yeah. It doesn't matter which 3. You just know the moment you tell me 3 of these, the fourth one has no freedom. Yeah?
Could we say that 10 is you like
No, degrees of freedom are how many things can be changed.
have order?
No order.
Which is
No
lost.
order. Not important. Yeah.
if we'll start from 3, we will end up with a 7. So 7 will have a degree of freedom. It will be,
If you started with this last one, is it?
yeah,
That could have a degree of freedom, so could that, then this one doesn't.
yeah.
Yeah.
So
Can we
show
know
a
number?
degree of freedom.
It can be anything. It can be, you could tell me this, this, and this, or you could tell me first, second, fourth, and then the third one has no freedom.
Okay, and can you repeat one more time where it's 7.84?
The 7.81? Yes, from the tables. I'll show you now. Question, yeah?
So essentially, does it
Hang on, one at a time. I'm going to show you in a moment how to get 7.81, yeah?
Essentially, the degrees of freedom is the number of hexagon minus 1.
For these simple tables, yes. Now, not always, though. Not always, but for our purposes, most of the time, yeah. Now, how to get the 7.81? You go to the column marked 5%, as always. That's 5%, can you see?
always?
Always, because remember last class we said
It's
5%. And you go to 3 degrees of freedom. In the 5% column is that number.
Okay, but if we'll took another order and we'll have a 7, like a degree of freedom, we'll have like another percentage, like, and it will change.
If you took another order.
Yeah, like from the, as I said, from 3 to.
No. I thought I was clear. Was I not clear? Like, I was clear. Yeah. It doesn't matter if you start from this side, you still have 3 degrees of freedom.
Oh my gosh, yeah, I got it. Sorry.
For the degree of freedom, isn't it? There's a formula like n minus 1.
No, I don't. It's that those formulas. No, yeah, they're not as helpful as you think because I find cause more confusion than yeah. Yeah. Hey. Come on. He's embarrassed for you, okay? Right. Continuing.
No.
What?
Is you.
You're thinking the same
That
thing.
makes the number 3 that confused because
Ah, yeah.
the issue, it's like different way of.
All right, was it only the 2 of you that were confused by that?
No.
I know, but
Imagine this is
the second time you explained it to me.
Yeah.
Okay.
I know what you're talking
Okay, so you needed it 2 times, fine. You didn't need it 4 times though. Okay, fine. Okay, that's okay. I can live with that, that's fine. Right, we'll do another example. Let me do the next species here as another example, okay?
Rejected or?
Rejected, because our 10.3 is too big. Yeah, too big. So actually what you've done now is you've provided evidence to the hypothesis that Colin made that these don't show up equally likely. In other words, the hypothesis that these are equally likely is rejected now. Okay. Did he, out of interest, did he give the reason why they're not equally likely?
about. Well, yeah.
Kind of.
Oh, okay,
Some
he did.
biological stuff.
Oh, it's a biological reason, is it? All right, okay. Thank you for not making it too technical for me. Okay. Right, let's have a look at another one of these examples. So whatever species PT is. So you have 6, 15, 4, and 8. And before we begin, the degrees of freedom is?
3.
Great, okay. No, not 8. Definitely not 8. It's 3. Right, so this is what we observed. Now let's see what we expected to see. How many do we have here in total? No, it might not be 23 again. What, is it 23? Say again? 33. Divide that by 4. What do you get?
Why did you put degree for 3 times 3?
One sec. Huh?
8.25.
8.25. Now you might say this seems a little bit strange because you could never expect to get 8.25, but this is how the calculation goes, so you put the decimal in. Okay? Now, what were you asking me, Hazza?
Why did the degree of freedom is 3? Shouldn't it be 8 or 6? No, you said like the number, the fixed number is 8.
There are 4 data involved.
This is like, I must have died and gone to hell. This is what happens to maths teachers when they go to hell. It's just, you get stuck in a loop. Hazza, really?
No, you
Really?
said it should be 8. And this is this like new example, right?
Yeah, new example.
Okay, the degree of freedom should be 8.
No! Degree. Can I explain it in Arabic?
I'm going to explain it one more time. And the next person who asks me, I'm going to, I don't know, it won't be pleasant. Right. Now, listen carefully, okay? If you were to repeat this experiment, could, for example, this number be different? Yes, it could. If you were to read this experiment, this could be different, couldn't it?
Yeah.
For example, maybe this could be different, couldn't it?
Yeah.
And maybe this could be different.
Yeah.
These 3 guys could be different. But as soon as you know these 3 numbers, you automatically know this number, don't you?
Yeah.
Because the total should be, what do we say, 33. How many of these 4 numbers can change? That is, how many of these numbers have freedom?
Yeah, I thought the
Shh,
fourth
don't speak
number-
anymore. It's okay. It's
No, I
okay.
thought the fourth
No,
number-
it's okay. It's okay. I know what you thought. Right, okay. Now, the degrees of freedom is 3. So, taking out the calculator, let's calculate the chi-squared here. What is it going to be? It's going to be 8.25 minus 6 squared over 8.25 plus, it doesn't matter which way around you do it because it's the sign cancels anyways, over 8.25 plus 8.25, yeah, that's a 15, isn't it? 8.25 minus 4 squared over 8.25 plus, I can know what that last one is, 0.25 squared over 8.25. So what is the chi-squared here? The total, please, yeah. Why 15? Which 15?
15.
Was 15? 15 was just given in the data. This is the data. This is given. It's from the experiment. Yeah.
But why did you put 15 and 4 or 6?
Which one? This one?
Yes.
That's the formula, the difference between the two. Remember? Difference squared over the... So what's the total here? What's the total here? Come on, what's taking so long?
I think I was just a bad person in the previous life, and this is
Possibly. Punishment,
interpretation
yeah.
of hell for you.
Must be, yeah. Surely I must have earned it by now. Right, what's the total here? 8 point... That's fine, what is it, 8 point... Okay, so about this. Now, what is it, 8.3, is it? Okay, it might not matter too much because it depends what the value was. What was the value? Okay, it's still bigger than 7.81. This is too big, so therefore reject them. Reject null hypothesis.
So,
Yes.
what if the two values are same?
We talked about that in the last class. We hope not for that to happen. They'll never be exactly the same because the problem is you're rounding here to 2 decimal places. Often when you do this in real life, the computer gives you more precision. And anyways, in the exam, I highly doubt they would put a student in this situation where they have to decide, do I or do I not here, okay? So it's not a situation for you to worry about. Yep. Okay.
1 second, please.
I think what would happen in real life is you would kind of fudge one of the numbers earlier. You would like round it down to make this like a tiny bit smaller. So you can say, yeah, so you can get whatever, basically you can get whatever result you want. You can fudge the number, round it up or down earlier to try and have it go whichever way you want.
Isn't it
Yeah.
square root?
Yeah, but this is real research. This is real life. This is what really happens, you know? Yeah?
Isn't it you have to square the number because it's
Yeah, we do. Squares in the formula, yeah. I assume when they typed this in correctly on the calculator, they got 8.33.
No, I mean when you get 8.33.
Hang on one sec, sorry, yeah? Okay. It might be a little bit off from that.
8.33 after square root.
No. I know what you're thinking because the square here, is it? Yeah. No, just think of this as a single symbol. The square doesn't really mean square here. I know it's confusing. It's just because of the name.
Yeah.
You see, like, it's because if you want, it's this, you know. Yeah. Okay. Nikita, what's wrong? What's wrong? Yeah, continue?
Yes.
Yeah. Now, there's a couple of things to point out about this chi-squared that makes it a little bit different as well to the binomial testing we did last time, okay? The chi-squared is much more reliable the larger your sample is. So you notice in this table, I think the highest degrees of freedom, it goes up to 100, okay?
Can you please remind why we use 5%?
It's just a convention. It's like a standard. It's not a rule. You know, it's a research standard.
So what do we have at the person?
No, well, yeah, you can just, again, round it to the nearest one. Because, is this our 5% column, wasn't it? You can see the difference between, for example, like 90 and 100 isn't really that much. Yeah, one sec. So 2 things I want to say. This chi-squared works much better the larger the sample is. And in fact, a lot of books will say you shouldn't be using chi-squared if any one of your observed numbers was less than 5. So technically speaking, it was a little bit bad of me to use a chi-squared test here because this number here was less than 5. Now, that isn't something to worry about in the exam. I'm just telling you this because chi-squared is something you can use a lot in research because you can understand there's a lot of experiments where you have to count something, like how many codons, you know. So technically speaking, you shouldn't be using your chi-squared if you're getting if one of your data points is less than 5, really. Okay, has it? Your question, was it?
Yeah.
What was it?
Why do you use this
Yeah.
Like, why do we need to use, like, to get what?
It's a hypothesis test. So I'll do another example, okay? I'll do another example.
So,
Yeah.
is there any such thing, one tail and two tail?
Not for this. Not for this. No. There's no one or two tail here. What you're doing is you're checking if your chi-squared is too big. Because chi-squared too big means that what you observed and what you expected were too different. The numbers were too different. And it's not two tails because the square in here means you don't care about the direction. You just care about if it's too different or not. Okay? Look, we'll do another example. Can I scroll down?
Yes.
Yep. So we'll do the example with the coin, okay? So I'll give you just a minute to try it quickly. I flip a coin 100 times and I get 60 and 40. I want you to write out the full process. So the first you state the hypothesis, then you state the alternative, degrees of freedom, chi-squared, and then you check if it's too big or not. Okay? This is what you observed. I suppose, Karul, you were asking me if it's two tails or one tail. Or someone was asking me over here if it was two tails or one tails, isn't it? Yeah, yeah. Technically, if you want to be more precise, there are always two tails. The chi-squared. You're always checking usually, is it fair and balanced or not?
It's 0, it's A, and what?
And degrees of freedom, Tom, is the first thing to write down, really.
After you have hypothesis, what was supposed to do?
Well, do the full calculation for me. So, null hypothesis, alternative, degrees of freedom, chi-squared, and so on. You got it? Yeah? So reject or not? Oh. It's just a difference. Reject, yeah?
No, wait.
Wait, Haz is going to tell us for certain now what the answer is. Reject or not?
No.
I think they are separate.
Yeah, well, so that's not reject.
I'm confused now.
Right, let's have a look here. So,
Reject.
Hazza, degrees of freedom is?
No,
Shh. Good man. Right, the null hypothesis is that the coin is fair, and then the alternative hypothesis is that the coin is not fair, is biased, yeah? No towards, it's just fair or not.
Is it?
No, it's always two tails for these, yeah. Okay. The chi-squared is, what were we expecting to get here? 50 and 50. So it'll be 10 squared over 50 plus 10 squared over 50.
4.
So that's 4. Now, is 4 too big or too small? Let's have a look. It's too big, is it? Is it much?
Yeah, 9.
Oh, just...
Oh. Isn't it 9 because we got 4? Or we just can't
What's the degrees of freedom?
1.
3.84.
Yeah.
Yeah, okay. So, this is more than 3.84. It's too big, so therefore reject H0.
Ah, okay.
Right? Not bad, really, is it? Coin is evidence that the coin is not fair. Yeah.
Another one?
Yeah, for sure. Okay, can I scroll down? Yeah? Has it? Yeah. Okay. Now, question 2 here. We'll do the calculation, but if we're being proper about it, why can't I really do the chi-squared on question 2? Question 2, is a die that's been rolled.
Huh?
Question 2 is you roll a die. So you can either get a 1, a 2, a 3, 4, 5, or 6. How many times did you get 1? 4, 4.
5, 3, 2, 6.
Why is it a little bit improper to use chi-squared here? Yeah, there's a few of them less than 5. Yeah. But we'll use it anyways. So, what is the null hypothesis here? Die is fair. And then the alternative is it's bias. Okay. And Dasha, the degrees of freedom for this problem is?
5.
Yes, okay, good. All right. Calculate and tell me if we reject or not here.
No, wait, 2.
No, don't annoy me. Okay. No? What was the total here, David? How many did I... Oh, good. That's easy then. So that's 4, isn't it? Yeah. So the chi-squared then is 0 plus 0 plus 1 over 4 plus 1 over 4, isn't it? Yeah, plus 4 over 4 plus 1. So 2.5. What's the difference between 4 and 4? Yeah. So,
Isn't it 1 over 4? 1 over, 1 over 2.
Just put the number.
Last one.
the last one, is it?
Yeah.
It's the difference between 6 and 4 is 2 squared. 4 over 4 is 1. Yeah. 2.5, isn't it? Yeah. Yeah.
But
So,
it's not 4 and 4, it's 4 and 3.
which one?
But still, you still accept.
Which one? Which one?
The 0, you said 4.
Yeah, this is 4. That's what we observed. And what did we expect? 4. We expected 4 for all of these, didn't we? Yeah.
Sorry.
Okay. Is this too big or not? What's it? 5?
So we don't.
Well, not. We don't say it's. Yeah. Okay. I know what you mean. It's not too big. It's. This time it's less than the value here, the critical value of 11 point. Isn't it? 11.07. Yeah. So therefore, we do. No, we would rather we say we do not reject H0. Yeah. Did you get that? Yeah. Now these ones are a tiny bit too easy for the exam, just a tiny bit. A more realistic exam question would be number 3. So I'll let you try this for a moment, number 3. Then I'll do it.
I have a question.
Yes.
If the answer 2.3 was like 6, do we reject or no?
If the answer is what?
Like 6.
What do you mean?
More than 5. Do we reject in this situation? Or do we accept?
Huh? If it was, which number are we talking about?
Yeah. The last step. Like we got 2.5, right?
Yeah, it's less than 11. Yeah. So do not reject, yeah?
We don't care like about the 5 thing here, right? Because the 5 is 11 now. When there's a,
I'm not sure what, I don't understand what you're saying. What 5 thing?
like when you say like if from 5% we reject or accept, right?
Oh yeah, yeah. So what are you asking me?
Yeah. So if
We only care about 5%.
so if 2.5 like for example was 6.1.
Still the same?
Yeah, because of the 11.
Yeah, because of the 11. Yeah.
Okay. Is there 200 students? Yeah.
Okay, do you have that?
1 second, please.
Yeah.
5.
No 5 minutes,
3.
come on. Maybe 1.
No, 3. Please.
Maybe, we'll see. Got it?
Oh, 1 second.
So, reject, okay. Reject? Or not? Don't know. Unknown. Reject or not?
Do not. Do not.
Right?
I guess do not.
Right, let's have a look. So, what's the null hypothesis here? That the grades follow a, what is it, a 10%, 20%, what is it, 40%, 20%, and 10% spread.
Yes.
The teacher's claiming that that's what percentage of students get the grades A, B, C, D fail. Okay, and the alternative would be not this. Okay, so degrees of freedom is 4. Total number of students 200. If this hypothesis was true, and 10% of students were supposed to get an A, we were expecting how many students to get an A? 20. How'd you get 20? 10% of the 200. 20% was expected to get a B, so how many is that? 40. 40% were expected to get a C, how many is that? 80. 20% were expected to get, so that back to 40, and 10% were expected to get a fail, which is back to 20. Do you notice how these grades... back to 20.
Oh, yeah.
Yeah. Do you notice how these grades, if you were to plot them A, B, C, D, fail, that they basically form a sort of this bell shape, a bell curve. So, yeah, that's something we'll look at in the next lesson anyways. So this would be typical of grades, that they kind of spread out like this. Now, let us carry out the chi-squared test. So, the difference between 20 and 30 is 10. Squared is 100. 100 over 20 plus 100 again, isn't it? Over 40, sorry, thank you. I'll just put the denominators in. 80, 40, and 20. 400, is it? 100 and 100. Right, so that's 5 plus, what's that, 2.5? Plus 5 plus 2.5 again, plus 5. That's 17.5? No, 20. 5, 10, 20, isn't it? Now, let us see if that's too, that's probably too big. No, it's not. What are we at? Degrees of freedom 4. Oh yeah, 9.49 only.
I have a question.
Yeah.
For the E,
Yeah.
just do like 200 divided by...
I just did 200 times 10%, 20%.
Why did
40%.
divided by 5.
Me
I
too.
still got the 20. So I want
You
to
did
know
200 divided by 5.
40, 40.
what's it for.
So
Is this, like, I just want to...
your expected values were different.
I just maintain like a 40, of course.
Yeah, so you've tested a different hypothesis.
But it's rejected still.
Yeah, but he's tested the different thing. I've tested if the grades follow a 10, 20, 40, 20, 10 spread. What has he or other people have done if they made all these the same? What have they tested?
Even spread of the...
Yeah, you've tested that the teacher has awarded an even spread of grades. Yeah. No, it's true. You reject that as well, but that doesn't answer the question I asked.
Alright.
Okay, because I got like the 20 as well.
There was similar numbers in the calculation by coincidence.
Yeah,
Yeah.
I just want to know. So
Yeah.
we just do this.
Yeah, this would be typical exam question. Typical exam question.
1 second, please.
Yeah, you're writing this down? Yeah?
Yeah.
Is that okay? Out of curiosity, how many people actually just divided by 5 rather than get the percentages? That's a bit concerning. Yeah. Correct. It's about this way is how we do this one.
Why did you do it this way? Because there is...
Because of what I'm testing. I'm testing that the grades follow this distribution. Remember, what you expect in the sense of what you expect from the null hypothesis. You know, so if you were testing that the grades were all equally likely, then you would expect all of them to be the same number. Yeah. What was that? 20, 20, 20, no, 40, 40, 40, yeah. Yeah. That is you testing that every grade is equally likely in the class. Yeah, I suppose kind of so, yeah. Yeah.
So when we put the numbers in the formula, isn't we add all the expected numbers and we divide them by 5 to get
these numbers?
All these are the expected numbers?
No, all these are the expected numbers, right? How do we get the top number? The difference, the difference between these two squared.
The difference or?
The difference squared. What's the difference between 30 and 20? Squared. The difference between 50 and 40? Squared. Difference between 60 and 80 is 20 squared. You get the idea? Difference between 30 and 40? Squared. And 30 and 20 squared.
But from where did you get the expected numbers?
Oh, where did I get them? Yeah. So I was told 10% of students get A's.
Okay.
There are 200 students.
Yeah.
What is 10% of 200? I'll tell you, it's 20. Yeah. And what is 20% of 200? Guess what it is? Yeah.
How did you calculate that?
How did I calculate that?
Quantitative.
I did thank you. 0.2 times 200. 0.40 times 200. Yeah. It's okay.
Oh, okay.
Yeah, okay. All right. Right. What I'll do we'll do the hard one together, and then I want to do some exam questions of this, and then we'll leave the rest to practice by yourself. So the trickiest one here is number 7. Yeah, well, you know how these things, you know how the workbook works. Yeah. Now, number 7 is actually a very important research example. The example in it is kind of made up. It's a silly example. It's about being left-handed or right-handed. But you can imagine many, many situations in biology, for example, where you would want to test something that's happening in number 7. I'll give you an example of what I mean, to be clear. So, some people will obviously develop lung cancer or not. And some people would obviously smoke or not. And you would like to test, does smoking have an interaction with lung cancer, for example, okay? Or you could maybe consider, do people who have high cholesterol and low cholesterol, and then people who develop heart attacks or don't develop heart attacks, is there an interaction there? Do you get what I'm saying when I mean interaction? Yeah. So, the example that's in the book is a silly example, but the structure is what you would see quite often. So here I want to ultimately know, is being male or female going to interact with whether or not you're right or left-handed? And the chi-squared is actually a way to test this, which is really, really useful. So you're in a position to answer research questions like, does A interact with B? Does A have an effect on B? Do you understand? Yeah. Like, I don't know, you can probably think of many biology examples. Like, for example, you're doing genetics at the moment, right? Yeah. So you might say, does the presence of this particular gene affect the chance that the person will get whatever disease? Do you get the idea? Yeah. Yeah? So, let's look at number 7 together. So what we have here is male and female, right and left-handed. And at the moment, it's kind of difficult to judge if being male or female affects whether or not you're right or left-handed. Let's have a look at the table here. Right or left-handed. Okay. Well, we need to make a judgment now in a second. Let's have a look. Yeah. Close. Close. Come on. Ready to continue? You're holding up the class. Now, if you look here, 43 males are right-handed and 9 are left-handed. 44 females are right-handed and 4 are left-handed. Just at a glance of the numbers, is it looking like being male or female is having any effect on whether you're right or left-handed?
No. Yes. No. Yeah.
Yeah, I think so. I mean, roughly speaking, there's the same number of males and females that are right-handed. Nikita, please. But there are twice as many left-handed males as there are females. However, you must keep in mind, though, there are more men in this group than there are women. So it's difficult to say confidently just from this if it has an effect or not. So we need to do the hypothesis test here, but I've broken the process down for you. So step 1 is just to complete the table. How many men are there altogether? 52, and here 48, and in total there's 100. And here left hands 13, and here 87. And again, that also adds up to 100. Okay, fine for part A. Okay, so that's part A. Part B. What percentage of people were right-handed? So percentage of people were right-handed. How many right-handed people are there? 87. So 87%. What percentage of people were left-handed?
30 over 100.
Yeah, 13 over 100, 13% are left-handed, yeah? Yeah. Okay, that's part B and C done. So here's the interesting part now. I'll put it in red here. If gender did not affect handedness, how many men are expected to be right-handed and how many are expected to be left-handed? So imagine that gender played no role in determining if you were right or left-handed. If a population had 87% people right-handed, then we would expect 87% of the men to be right-handed and also of the women.
Yeah.
So how?
Yeah.
Half.
No, think about this. If I said in this classroom 87% of people are right-handed, and then I separated the class into boys and girls, I would still expect 87% of the boys to be right-handed and 87% of the girls to be right-handed. If there's no effect from gender.
50.
Okay. Why are people giving me numbers randomly? I'm not asking for a number. Yeah. I just want you to get what I'm saying, if you understand it. Do you? Because you're giving me a number.
Can you just
Continue.
repeat?
Yeah. So, imagine that 87% of people are right-handed, like in this class. Okay. Now I separate the class into 2 groups, boys and girls. What percentage of the boys will be right-handed? And bear in mind what I told you 1 minute ago. 87%.
Yeah.
And what percentage of the girls will be right-handed? 87%. Okay? Because I just told you at the very beginning 87% of people are right-handed.
Okay.
Okay, it doesn't matter about the gender.
And if gender doesn't matter, so it will be like 40.
If the gender did matter, then perhaps I would see differences. For example, maybe 90% of the boys are right-handed and 80% of the girls. I don't know. That's if gender mattered. But remember, I'm saying if gender doesn't matter. Okay? So 87% of people are right-handed. Okay? How many men are there? 52 men. Yeah? Calculate for me, please. What is 87% of 52? Right, so what I'm going to do, I'll just put it in the same box. Here. There are 43 men, isn't that what I said? But how many did we expect to be right-handed? 45. 0.2. Okay, I'll just leave it at 0.2 because I'm out of space. Okay. Now let's repeat for left hand. So it was 9, but what is 13% of 52?
6.8.
6.8, is it? Okay. 6 point what? Okay, 6.76. We'll do 3 significant figures, okay? Now, let's repeat for females. 87% of the 48, please. 41.7. So if I do 3 significant figures, 41.8. And then lastly, 13% of the 48. That's 4. I'll read the numbers out. And 6.24. Okay, so expected was 45.2, 6.76, 41.8, and 6.24. Now, at a quick glance, is the numbers quite different between what I observed and what I expected? Well, how many men did I observe that were right-handed? 43. And how many did I expect? 45. Not a big difference. A bit more of a difference here. I expected 6.76, but I observed 9. This one probably is big enough. 44 and 41.8. And lastly, 4 and 6.24. Okay? That's D and E I've answered. D and E I've answered. I've put it into the table here. Okay, F now. Now, this is where we have to think carefully. What is the degrees of freedom? And remember, the totals are fixed numbers. And this puts a restriction on the freedom inside.
Just one? 3.
Yeah, just one, correct, yes.
Why 1?
Yeah.
Just one.
I'll explain now. Question, yeah?
Left-handed males is 6.76. No,
That's what I was told.
in the book.
Oh, it's a typo, is it? Okay. Yeah, that's a typo. That's a typo then. Okay. Right. Oh yeah, so degrees of freedom now, I was saying. Oh yeah, thank you. I'll fix that. Right. Oh yeah, degrees of freedom. Okay, let's start here. Could this number vary? Of course.
Yeah.
But the moment I know this number, I automatically know this number. Because the total number of men is 52. So there's no freedom here. Now, the moment I know this number, I also know this number. Again, totals are fixed. Total number of right-handed people has to be 87. So is there any freedom here? No. Now, again, likewise, once I know these 3 numbers, I definitely know this number because the total should be 100. So really, the moment I tell you one of these, the other 3 are known. You know, I'll give you a clear example to demonstrate this. Watch this table. So, I'll just say here, 5, 5, 10, 6, 4. And here's the data you collected here. Okay? There's the data. Now let's pretend I give, huzzah! You're going to ask me in 1 minute, teacher, how come the degrees of freedom is 1? Could you repeat that? And I'm not going to, okay? So, in this example here, let's suppose I give you the first number. I say it's 1, for example. Okay? No, because I'll say it's 2. Right, I'll say it's 2.
3.
You automatically know this number. It has to be 3. And you automatically know this number. It has to be 4. And you automatically know this number. It has to be 1. Yes?
Yeah.
So how many of these can truly change? Only this one. The moment you know this, the other 3 fall into place. There is only 1 degree of freedom. Okay, good. Right. Degrees of freedom equals 1. Okay, now, what's next? Probably calculating the chi-squared, is it? Yeah. G. Right, chi-squared. It's 1, 2, 3, and 4. What goes here? 45.2, 6.76, 41.8, and lastly 624. And on the top, you can do it for me. It's the difference is squared. So tell me what you get here, please.
The first answer is 4.84 over 45.
Okay, well, you can just give me the total when you finish there, please.
$1.769.
1.769. Now, think about this, please. Remember our guiding principle here. The null hypothesis is the non-special hypothesis, right? Null hypothesis, not special. So what is the null hypothesis here precisely? And remember the principle. It should be not special.
100.
Not special.
Since when is 100 a sentence? Yeah, give me null hypothesis, please. What is it?
Greater.
That's fine. Yeah, you can say gender has no effect on left or right-handedness. Yeah.
Ah, okay.
Yeah, what's another way to say that? That's fine, by the way. I wouldn't say correlation necessarily. You know, yeah, perhaps that. You could. The simplest way to say it is right or left-handedness is independent of gender. And the alternative is that it is not.
It is dependent.
Yeah, there is a relationship, an interaction. Now, let us look at the tables. Yeah,
In the brackets, it's the difference between the 45.2 and
the 43 and the 45.2, yeah. 1 degree of freedom, 3.84, more or less than 3.84. Sorry, yeah, so I'll have to put it the other way. Less than 3.84, so reject or do not reject. So we do not reject the null hypothesis. What does that mean? What we're saying is that we don't believe that gender has an interaction with left or right-handedness. In other words, your gender doesn't play any role in determining if you're right or left-handed, in making it more or less likely. Okay? You can imagine doing this exact type of analysis with, for example, here could be smokers and non-smokers, and developing cancer and not developing cancer. And then you could answer whether or not smoking has an effect on developing cancer or not. And in fact, the statistics you're doing right now was developed for biological purposes about 100 years ago by the biologist Fisher. You wouldn't have done him in your course. Fisher developed this binomial test we're doing, okay? This chi-square test we're doing. These were all developed by a biologist 100 years ago to answer biological research questions like, does smoking affect your rate of cancer, for example? Okay? And it does. Yeah?
It does?
Yes, smoking affects the rate of cancer.
Yeah.
Yeah. Yeah, question, Karul? No? What's wrong?
I mistaken the answer.
Okay. Yeah. This stuff is also important in genetics, for example, things like this. Yeah?
The XY thing, the square XY, I guess.
Which one?
That the probability of like getting something.
Yeah, for the tables. Yeah. Yeah. Which one? Yeah. Do I have the wrong number total? Yeah, what should it be? Oh, the reason it's wrong is because the table had a typo in it. Yeah, thank you. Thank you, thank you. Okay. Right. I want to have a look at an exam question. What does this look like in the exam? So we can open up Moodle. I have it here actually. Let's look at last year's exam. See if it's in it. Why? It might not be in it. It's in some of the exams.
I don't know, probably section B.
Oh, it's definitely section B. Here we go. Okay. Right. I'm going to let you try this one before I give you the answer. Okay? So, a sack holds a large number of bulbs of different colour. The labels on the sacks claim that the numbers of red, white, purple and yellow are in the ratio of 1, 2, 3, 4. 100 bulbs are selected and the colours recorded. State your hypothesis.
It's 0.
Yeah. Why is there 2 marks here?
Because it's 0, it's 8.
Exactly right.
No,
Work.
and alternate.
Yes. Work out the expected number of each colours and then carry out the test. Now this test is quite unusual because they ask you to carry it out at the 10% level, which is actually not proper of them. It's proper to do this at the 5% level. Okay. I'll give you a minute to try this. I think you can get it.
Still we need to go to 10%.
Yeah, we need to go at the 10% one, which is now this one here. Okay? Go, Hazard, go, come on. Whose is this? Can you pass? Who gave me this? Thank you.
I want to bring it, but it's too far.
Just worry about your question, please.
Don't try to be nice.
I'm not trying.
It just happens naturally for him.
Thank you. It's not confused, I just focus.
This is the same as the mark. Fail.
It's very similar to it, correct, yeah. Alright, we got this?
No.
No?
What's the expected number of each color?
Yeah.
Is it the E0 and the E?
Hmm?
The O, E?
It's the E they want, yeah.
Okay.
I got that one, so I got one more.
It's easy, but how many marks? 5, 8 more? Oh my god. That's A and B.
What's your hypothesis?
Hypothesis follows the one and otherwise it is like follows that one.
Got it? So reject or not?
Wait, I need more time.
I'm confused. I'm just waiting to say color.
No, it's easy. Don't speak. You know what she said? She said, like, you annoyed my mother.
What? You annoyed me. You're annoying.
You just tell her, chub her face. Alright? Alright. Continue?
Yeah.
Yeah. It probably just means there's some weather blowing in.
This side's rain, this one not.
Perhaps. Alright, let's have a look here. Do you have it down?
Yeah.
So, a sack holds a large number of bulbs of different colours. The labels on the claim that they're in the ratio of 1, 2, 3, 4. State your hypothesis. Okay, so let's have a look at the first one here. The null hypothesis that the
All of
colours are in the ratio of 1, 2, 3, and 4 as claimed. And the alternative would be that they are not, basically. Okay, so that's 2 marks in the bag. Next one is work out the expected number. How many bulbs are there? 100. So the ratio should be 10, 20, 30, 40. That was what you expected to get. Are these in the ratio of 1, 2, 3, 4? They are. 10 to 20 to 30 to 40 is in the ratio of 1, 2, 3, 4. And do they add up to 100? Yeah. And did you forget how to break a number into the ratio of 1, 2, 3, 4? If so, you need to contact your elementary school teacher, because this is when you learned how to do this. Isn't it? I remember these questions. You have 10 sweets, and you want to share the 10 sweets in the ratio of whatever. You remember these from elementary school? Yeah.
The ratio 1 and then multiply by.
Yep, exactly. Yeah. Your elementary school teacher will be proud of you. Okay. Now, next part is let's carry out the chi-squared test. So,
now we divide by 4.
no. Ratio. Do you know how to split a number into a ratio? Okay, I'll let you look that up in your own time. Right. So what is the first one? We expected 10, and how many did we observe? 8. The difference is, so 4 over 10, 20, 30, and 40. The difference between, that's a 9. Difference between 30 and 9 again, okay? 16.
Squared, right?
Yeah, they were all squared, yeah. Yeah. And what do we get here? Sorry, what is it?
1.55.
Right, degrees of freedom? 3. And too big or too small? Probably okay. Well, not too big. Wait, at 10%? 6.25. Ah, yeah, it's definitely okay. In fact, it was even okay at, it's even not okay at 5%, wasn't it?
Yeah.
Yeah. So, yeah,
The question when they say 100%, what do they mean?
100%.
10%.
We just changed
Oh, we changed we don't use the 5%, we use the 10% one. Do not reject H0. So, the last part here was, what conclusion can you draw? So what is the conclusion here?
The label is correct.
Yeah. Yeah. The label is correct.
This is a question.
Guys, did you get that? You did? How many marks is this question?
8.
It's a lot. It's a lot.
It's just a section we can choose.
The we've done this part, haven't we?
Yeah.
When?
Calculate the expectation and the variance. I think this is a good question in the exam. Already we can do 2 parts of it. And in a moment, or soon we'll be able to do part B and C when we do normal distribution. Okay? So, I just want to... Shh, please. I just want to put this into a context here. So, something else for 8 marks. Find the equation of this line L, and this line L is probably normal or something like that, and then they ask you to find the area. A lot of work or a little work?
A lot.
How many marks?
8.
I'm trying to
No.
8.
Yeah, I'll never do this. Like,
Yeah, 8 marks. Whereas the chi-square test you just did, how many marks? 8.
But it's divided.
But it's easy, like.
And in fact, it's even better because it's divided. It makes, it means that if you make a mistake, it can be a little bit more contained.
but this one easier. Yeah.
That's okay. Like, for example, suppose you get your hypothesis wrong here. Okay, you lose the 2 marks. But does getting this wrong in any way affect this calculation? No. It doesn't, does it? And it doesn't affect most of this, except for the last part. Suppose you got these the wrong way around. Then would your conclusion be right or wrong here?
Wrong.
It'd be wrong, because you'd be saying do not, what do we say? Do not reject H0. But if we got these the wrong way around, then we'd have the wrong conclusion here. Okay? So, it's kind of good that it's broken down, because it means your marks can be a bit more contained. Yeah?
How will we have mid-semester 2 exam?
Oh, I don't know.
26 of me.
No, whenever I want.
Mid.
No, I think it'd be a good idea at some point to have one.
Maybe April.
April?
Yeah, April is.
April?
So we have more
How about June?
like a lot.
Yeah, April.
Maybe a week before the exam, like a mock exam.
Yeah, maybe. We'll see.
Is this next?
Not this year.
I'm only talking about maths, man. I only care about maths. Right, okay. That's what an exam question looks like. You can see it's actually, once you practice a couple of them, a pretty straightforward exam question.
Yeah.
So I want you to try the workbook one. If you can continue from, what is it, 4? 4, 5, and 6. Can you do those now? You should get them done now.
4, 5, and 6.
That's what I said.
Just making sure.
Now that you're sure, you can start.